Okay, now we are going to stabilize our circuit, and we're going to stabilize the amplifier. And the first thing that we should try is to see if we can put a phantom zero, because that will be the less intrusive way to do the stabilization and the easiest also one to implement in practice. So I will work on with the first two poles that are at low frequencies. This is the third pole. This is a quite high frequency. So let's try to work with our low frequency poles, and then I'm going to use the ones that we calculated, okay, that are pretty much close. So I'm going to use these two, and let's see if we can put these ones in Butterworth positions. So let's see, phantom zero compensation. Okay, so first I have to check if it is possible. Check if it is possible to add a phantom zero. So for that I have to make sure that P1 plus P2, this one have to be lower than the maximum achievable bandwidth, that it is omega n. So let's calculate this, P1 plus P2, that it is going to be equal to 3.04 megahertz if I take the values that I calculated. For two poles, omega n is going to be equal to the square root 1 minus AB0 times P1 P2. Then when I replace the values that I just calculated, that will give me 31.4 megahertz. And the square root of omega n, that will give me 44.4 megahertz. Okay, so then I can see that 3.04 megahertz it is lower than 44 megahertz. Then it is okay. I can go forward and do the calculation. Then where to put the zero? We have an expression for the zero in the case there is a two-pole system, and that is the zero will be located in omega n square P1 plus P2 plus square root of 2 omega n. And remember that these are the negative values. P1 and P2 are negative. They are always below zero. So when I plug in these numbers, I will get that that will give me a zero at minus 20.8 megahertz. And then now I go back to my circuit here. When I want to put a phantom zero, the capacitor that I want to add, it will be here, C compensation. So this will be in parallel to R2. That will produce a pole in the asymptotic gain that will be converted in a phantom zero. So let's calculate the value of that capacitor. That zero will be equal to 1 divided by 2 pi R2 times C. Then that means that C is going to be 1 to 2 pi the R2 zeta, and that will be equal to 37.1 femtofarad. That means almost 40 femtofaraday, and now let's go and test it. So we go to cadence, and we can delete this here. So I have placed here a capacitor in parallel to the resistor that in my schematic is R11, but in our calculation is R2, feedback capacitor. So I will connect it. Okay, and then I will put exactly the value that I have just calculated. Let's see, that will be 37 femto, and let's just run the simulation. Okay, it is done. I will check it, and then let's take a look what happened. We take the closed loop gain, and okay, we see something nice has happened. Now I don't have any more that horrible peaking that I had before, so it is much more smooth, the frequency response of the circuit. And if you check the position of the poles, now they are at first they are stable. They are in the left hand side as I expected, and they are at -20 megahertz and -28 megahertz. And yeah, they are not exactly in Butterworth positions, but remember that we have a third pole around. We didn't take in considerations zeros that come from feed forward and other high frequency poles and zeros that might be around, so just we took the assumption that we have these two poles. So actually they did a pretty good job. Now we can actually adjust these poles a little bit. So but before that, let's take a look to the rod locus. Now look how beautiful it is. Before these two poles were crashing in the center and then moving to the they were moving towards the right hand side, and they passed the right hand side, becoming unstable. Now they are moving towards the left, close to the Butterworth positions. So our phantom zero is effective. It is working very nice. Let's try to tweak a little bit the value of that capacitor so we can get a better result. Let's move it to, let's say, 50 femto. Let's run simulation again. Okay, the simulation is done. Let's plot it, and then let's take a look now. Closed loop gain. Now we have a single pole that is located around 30 megahertz, and then we have two poles at 37. So we have actually three poles that are rather close by that are interacting. So it's not that we have a two-pole system anymore. We have three poles, and we have only one phantom zero trying to manipulate three poles. So there are three dominant poles that we have here right now. So it's a bit more complicated, the problem. But we see we are getting a reasonably good bandwidth, and actually very close to what it is predicted by the equation. No? We predicted that bandwidth of around 30 megahertz, and now we are having around 29.6, the closest pole. Let's try to see this in logarithmic scale, and then we see that we have a bandwidth of around 30 megahertz. So it's pretty good. Then something else that we can say here, let's see, in the loop gain. In the loop gain, we can take a look to the phase also here. Let's put it this one here, and let's move this figure here so we can see both phases and amplitude of the loop gain there. And then let's put a vertical marker here, and then let's check when the loop gain becomes 1. Let's check what is the phase that we have there. So that will be 1 there. You can see it is around here. Okay, so we have around 1. The loop gain is 1. We have a minus 131 degrees. This is around 60 dBs phase margin. We have to subtract 1 from 180. Sorry, this is 50 degrees phase margin. Around 50 degrees phase margin. So that after we did the composition, this is using classical stability theory, checking the loop gain and the phase. Okay, so we can also double check with this one. But typically we will want to see the final position of the poles that we have here. Okay, very good. So we have done the stabilization with the phantom 0. That it is our first option for doing stabilization. Okay, we're going to disconnect the circuit, and then we are going to try to do the same, but with pole splitting.